All right, let's jump right into this explainer on OpenAI's GPT 5.5 release. We aren't just looking at another incremental software patch today. We are looking at a fundamental shift in architecture and deployment economics. I'm going to run this exactly like a technical lead briefing a team of engineers. We really need to get under the hood, unpack what this model is doing, see how it completely redefines the benchmark landscape, and most importantly, figure out what this means for your enterprise budgets. Here's our roadmap for today. 1. Self-optimizing infrastructure. 2. Shattering complex task benchmarks. 3. Scientific and mathematical breakthroughs. And 4. Enterprise pricing and economics. We're going to build this from the ground up, starting with bare metal infrastructure and working our way all the way to API costs. Starting off with Section 1, self-optimizing inference infrastructure. Let's look at the bedrock here, because this is arguably the most groundbreaking part of the entire release. So, here's the million-dollar question. How exactly did OpenAI manage to match GPT 5.4's per token latency while dropping a significantly larger, much more capable model? If you know the stubborn physics of machine learning, you know that pushing heavier weights through a compute pipeline usually takes more time. So getting parity in serving speed while making a huge jump in intelligence, that requires tearing the inference stack down to the studs. Well, the foundation of this speed comes right from the hardware coordination. OpenAI didn't just take an off-the-shelf model and dump it onto new servers. GPT 5.5 was completely co-designed for, trained with, and served directly on NVIDIA's newest GB200 and GB300 NVL72 systems. It's absolute hand-in-glove integration, making sure the memory bandwidth is perfectly tuned to the model's exact architecture. But here is where things get really wild. The model actually optimized itself. Historically, humans used fixed chunking to split workloads across GPU cores, which involves a lot of rigid guesswork. Instead, an internal version of GPT 5.5 analyzed weeks of its own production traffic data from codecs. Then, it wrote custom heuristic algorithms to dynamically figure out how to partition its workload across the hardware cores. It literally analyzed its own traffic to write the code that makes it run better. And the results? A token generation speed jump of over 20%. That hardware coordination and custom algorithmic partitioning is exactly why we aren't seeing a latency hit. For engineering teams, this is a massive paradigm shift. AI isn't just living on our infrastructure anymore. It's actively designing and optimizing its own hosting environment. Moving on to Section 2, shattering complex task benchmarks. Let's step up to the execution layer and see what this optimized engine actually achieves. Take a look at Terminal Bench 2.0. This tests complex command line workflows requiring actual planning and tool coordination. GPT 5.5 hits 82.7%, completely crushing Claude Opus 4.7 by over 13 percentage points. When you're evaluating tools for your dev team, a gap this wide is the difference between a model getting stuck in a bash loop and a model actually resolving an infrastructure issue all by itself. But here's the kicker. Across these long-horizon coding tasks and real GitHub issue resolutions, GPT 5.5 achieved these dominant scores while actually consuming fewer tokens than GPT 5.4. Developers are calling this conceptual clarity. Instead of meandering through thousands of tokens of trial and error, it plans better, it's more direct, and it executes way more efficiently. And it's not just coding. On Genebench, which tests multi-stage scientific data analysis, it jumped from 19% up to 25%. Now, in the traditional software world, 25% might not sound crazy. But in quantitative biology, where these tasks normally take human experts days to complete, this is a tremendous leap in autonomous capability. We really see this model flex its muscles on those long-running problems. The data shows that the performance gap widens significantly during multi-day workloads, explicitly separating itself right around the 15,000 token output mark. Where older models would just lose the plot or forget the original constraint, GPT 5.5 stays totally locked in. All right, Section 3, scientific and mathematical breakthroughs. Let's look at how these abstract benchmarks translate into real-world scientific utility. This is where it gets genuinely paradigm-shifting. An internal version of the model didn't just write code about math, it discovered a rare combinatorial math proof for Ramsey numbers, and it was fully verified in lean. And over in biology, it allowed immunology professors to take an incredibly dense dataset, 62 samples, nearly 28,000 genes, and spit out a full research report in a single session. That is months of analysis condensed into hours. Brandon White over at Axiom Bio summed it up perfectly. He said, If OpenAI keeps cooking like this, the foundations of drug discovery will change by the end of the year. For the pharmaceutical sector, the ability to rapidly parse 28,000 genes completely changes the underlying speed limit of scientific discovery. Let's wrap up with Section 4, Enterprise Pricing and Economics. Time to talk budgets and the reality of deploying this architecture. Look at this spread on the API pricing. GPT 5.5 is undeniably in a premium pricing tier. $5 per million input tokens, $30 for output. That is exactly double the rate of GPT 5.4. When you compare that to highly aggressive pricing from competitors like Minimax at 30 cents or Xiaomi at $13, OpenAI is making it crystal clear. Top-tier intelligence comes at a steep premium. So how do we justify this to finance? We calculate total cost savings based on that token efficiency we talked about earlier. Yes, the raw per token rate doubled, but if a competitor's cheaper model takes 3 times as many prompt iterations and spits out twice as many useless tokens to fix a codex task, your total net cost with GPT 5.5 might actually be lower. You're paying a premium for a straight line rather than a discount rate for a maze. I'll leave you with this thought. We just watched a model analyze its own traffic and write custom partitioning algorithms to run 20% faster. If a model can optimize its own inference stack today, what happens in a year when AI fully designs its own hardware utilization and networking topologies? It's a fascinating, maybe slightly intimidating future to prepare for. Thanks for tuning into this explainer, and definitely go audit your current API usage to see how this new efficiency equation might play out for your own team.